Okay. Oh. Okay, let's say, okay, are we ready to go? Okay, let's say we've got an object, we want to get it to rotate, and in order to do that, we use this idea of a torque. If you think of a torque, best example would be like a nut with a wrench on it, and you have some length of handle, which we're calling R, the torque radius, and then we would, to get the most torque on this thing, we would want to apply that force perpendicular to the handle, and then that's going to give us a torque that's going to start to get this thing to accelerate. Imagine the axis of rotation is right here, and it's going to start to rotate around this point. Now, how that, this is what we would call the torque applied to this thing. In this case, it would be the net torque. It would be R times F perpendicular. I'll get more into torques as we get along, but let's just kind of look at this basic idea of why it's useful for rotation. Imagine this nut is kind of like welded on this thing. It could be like this big steel plate, and it's got some axis of rotation. Then we can tend to look at, again, these little pieces. Let's say this is the m sub ith piece and the m sub jth piece out here. They all are different radii. This would be R1 or R sub I, and this is R sub j. And again, you can imagine doing it to all kinds of masses on this object. Now, the idea is that ultimately everything comes down to forces. I take and I apply a force here. Now that force is in a kind of lever-like action is going to be applied to all these individual little pieces. They're going to get their little force that's going to start to accelerate these things. I'll call this F sub I, and then there'll be this one. These are going to tend to want to rotate perpendicular to the axis, so there's going to be, this is again F sub j and F sub k, and we could play with all of that. And the idea that the net torque gets distributed over all these little pieces, and there's going to be little individual torques going to go in the with the force. And I could say that net torque is the sum of all these individual torques, R sub I times F sub I. And that F sub I should be is going to tell me about the acceleration of this thing. So that's going to be R sub I times F, which should be M sub I times the acceleration, A sub I. And these accelerations are all going to be different, and I know that acceleration is going to be equal to R times not omega but alpha, the angular acceleration. This is kind of where we first started in our description of motion. So I can put in for that acceleration, that's R sub I, M sub I, and then acceleration is R sub I times alpha. And alpha is going to be a constant. That's why we want to use these rotational terms. All of these things are going to go and start accelerating differently, but they're all locked together as a solid object and are rotating with some angular acceleration, alpha. So it's starting to speed up. And the alpha is going to be the same for all these pieces. So I can say the net torque is equal to, I can take alpha, and then I have the sum of R sub I squared times M sub I. Oh, and that shows up again. What is that? That's the rotational inertia for this. And so we can write that as the net torque is equal to I times alpha. And so this is very similar to F equals ma. If you think of F equals ma, instead of the acceleration, we've got the angular acceleration. Instead of the mass, we've got the rotational inertia. and instead of the force, we've got the net torque on that. So this is kind of playing the same roles, F equals ma, as far as getting this thing to move. Okay, let's say let's jump into a problem. How about well, I'm pausing. I'm thinking let's do number 3 on the practice problem is probably a good place to start. Where we just have, let's say we've got a disk. It's rotating on its axis. We're going to hang some weight on here, m, small m. In fact, I might kind of avoid the numbers and just stick to symbols. This mass is going to fall and is going to start to accelerate, and then this thing is going to start to rotate. And let's figure out what's going to happen. We've got kind of a two-body problem. The idea that gravity is going to pull down on this thing with small m times g. What's holding it back from just going into free fall is that there's some tension. That tension is going to be pulling on this piece, and it's got a radius r, and it's got its the tension is pulling at a right angle. So I can see very quickly, like this wrench handle, I can see that the torque on this thing, the net torque on the disc, is going to be T times that radius r. And that should be equal to the moment of inertia of this thing, I times its alpha, the angular acceleration. Now, as this thing starts to accelerate, there's going to be a tangential acceleration. We kind of talked about this earlier. Tangential acceleration is going to be equal to r times alpha. Now, tangential acceleration would be a point on the rim of this thing as it's accelerating. Now, we've got a string wrapped around there, and we're assuming the string isn't slipping. And so the acceleration of that string, also the amount of string that goes down, whatever comes down here, this goes down the same amount. Whatever velocity this comes off of here with a tangential velocity, it's going to be speeding up, but at some instant the tangential velocity should be the same as the velocity of this thing going down. And the acceleration, that is the tangential acceleration, should equal the acceleration of this thing going down. Got a lot of red here. Let me get back to the blue. This thing is obviously going to go down. This thing is going to rotate. And I think the simplest way to avoid problems with this is to maybe, let's just call down the positive direction. And we can take a look at, and that would imply this is going positive as this goes down. That means this is going to go in this direction. Let's call that direction positive. We could have done it opposite, but I think that's a good intuitive place to start. Then we can look at this and we can do, this is a good old F equals ma on this piece. This is old hat. This is going to be the plus direction, so the sum of the forces have to be equal to just mg in the positive sense minus the tension. And then that should equal this one's mass, the little mass times acceleration. And that's what's going on here. Be careful that you don't say, oh, the tension's equal to mg. If the tension was equal to mg, would this thing even move? No, I expect mg had better be bigger than the tension if the thing's going to move. And the fact that the tension is not mg, we don't want to say, oh, this is mg on this thing here. That will be whatever tension we have. I've got a couple of unknowns here. I don't know the tension and I don't know the acceleration. I need some other information. All of this was based on this little block that's here. If I want to focus on this thing, this is where I want to again go to t equals r I alpha. The tangential acceleration is equal to r alpha. What we can do with this expression is we can say the net torque, which is T times R, is equal to I. Now this would be I of a disk, and he would state this in the problem, but I think you maybe know if you've done enough homework problems, 1/2 m r squared is the moment of inertia of the disk times alpha, and it's often convenient we'll write alpha as A tangential over R, and as long as the string doesn't slip, A tangential will be equal to A. So something that works out kind of nicely with these R's. Notice this R will cancel with one of these. This R will cancel with the other one. And we can come up with the idea that the tension is equal to 1/2 m, and A tangential should be the same as A, so I can go ahead and write that. So this is coming off of my rotational object. This came off of my mass that's moving down. And I can tie these two together. Again, I've got two unknowns. I don't know the tension. I don't know A. But I could go ahead and solve. Why don't I take this one for tension and solve in here? So I'm going to have mg minus the tension, which is 1/2 m. Oh, be careful with my m's here. This is a big M, the mass of this big disk. And this is small m, the little hanging mass there, so I better be careful. So I'm putting big M in here, times A is equal to small m times A. And anyway, you've got the numbers there. You can stick it in. It's a matter of solving for that. Well, I'll do a little more here. mg is equal to m minus 1/2 big M. Oh, take it over to the other side as a plus. Saying this doesn't look right. Times A. Or the acceleration is, let me write it over here. A is equal to mg all over m plus 1/2 big M. So this would describe the acceleration of this mass as it falls. Careful reading here. He said, in the question, he says, what is the angular acceleration of the cylinder? So he really wants the angular acceleration. He wants alpha. But we could go back to this idea that A, which is equal to A tangential, is equal to R times alpha. And so we can get alpha is just A over R. So once I have A, we just say alpha is equal to A over R, and we've got that. Okay, so that's probably a good place to start. Problems can get a little trickier. Let's do a little trickier one here. Let's say, how about number 5? Yeah.
So if he asked for the moment of inertia and the tension in the string, then would we just, then he would have to give us the acceleration, right?
Okay, yeah, you're kind of strategizing what you might do. We do have kind of two sets of equations for this guy and this guy. And it's leading to really two separate equations. And so we consider you can have two equations, you can have up to two unknowns if you're going to solve for it. I've just got all the symbols here, so you could imagine any one of those things you're going to actually have to solve for. But he would have to give you the rest. So that's why I kind of prefer to leave it in this form, and then we can either take the numbers he's given us, stick it in, and get what he wants, or you can start to play games like you're suggesting, where you can say, well, maybe he wants the moment of inertia. Doesn't want that. So all of that really comes out of the algebra. The basic physics setup would be the same, and you would go ahead and use symbols like I'm using just to represent these things, even like a T and an A, and I don't know what they are yet. So I just pretend like I do and carry them along, and then hopefully things are going to wash out. Okay, let's try a number 5, and that's similar here. It's where we get these things tied together. So similar to the types of problems we've been doing. This number 5, we've got a we got a 37 degree, and we've got this big pulley here, and we got this 5 kilogram mass, and we got a hanging mass here. And let's just call this M, and it's got some kind of radius that's going to be attached. And we can go ahead and look at forces. We could do separate free body diagrams, but with the colors, I think I can kind of fake it and you won't get too confused. I'm going to have gravity pulling down on this one. That's going to be 4 times G. 4 kilograms times G would be the force down. Then there's going to be a tension up here. And that's going to be pulling down on this one. There will be a tension. Also, gravity here is pulling down, and we're going to have some components to gravity. In fact, this component to gravity coming down the hill wants to pull it back this way. We're also going to have some tension, and on this pulley, tension pulling back. Okay, now, are all these tensions the same? Oh. Yep. Okay, now we have been playing that kind of game in our earlier problems in earlier sections, and that was when they said the pulley was a massless, frictionless pulley. It turns out that if you got a real pulley, if these two tensions were the same, would this pulley rotate? Right, it wouldn't rotate. So there has to be a difference in these tensions. Let's say that this is on this side T1 and this is T1. On this side this is T2 and this is T2. So we want to consider that we need to include that. This is going to be 5 times G down this way, but we want this component of the force F in the, let's see, getting ahead of myself here. Let's make some decisions about axes and directions. When you start a problem like this, which way is this thing going to move? Wow. Okay, this is going to go down, and then this is going to slide up. Now, it's possible if this was like 1,000 kilograms, you know, it might move the other way. So sometimes we can't tell with the math. The nice thing about the math, it'll tell you. What you do is first establish a sign convention, and I think this is the best way to stay out of trouble. I think it is pretty obvious this thing's going to go down, so let's call this the plus direction, and have everything related to that. So if this is plus, that means that this would have to rotate in this direction, we'll call plus, if it's going to go down. And then this one would have to go up in this direction. That would be plus. So this, so again, plus this way, plus, and plus. So we don't have to do this, but I think it's the best way to stay out of trouble. Now we will look at these individual pieces, and this is the plus direction. So some of the forces are going to be 4 kilograms times G down, minus T1, that's up, so that would be as a negative, is going to be this one's mass, 4 kilograms times the accelerator times G. Duh. Wait a minute. 4 times A. I had it right. 4 kilograms is the mass times the acceleration. That is the net force. I sometimes forget the obvious. Okay, now here I've got 2 unknowns. I don't know T1. I know T2. Okay, so that's 2 unknowns. Let's go over to this guy. I'm calling this way up. I'm assuming this is frictionless, I think. Okay, good. Got enough to deal with right now. Frictionless, so the sum of the forces in this direction, in the X I'll call going up, is going to be equal to T T2 is pulling up, but gravity is pulling down, minus 5 times G is pulling down, but then it's at this angle. If this is 37, this should be 37. You should be good with this now, times the sine of 37 degrees. And that should be equal to, F equals ma, this one's mass, 5 kilograms, times the acceleration. And they would share the same acceleration. Okay, so here I've got T2 is an unknown, and A is an unknown. So far I've got 3 unknowns in 2 equations. So I need another one. Okay, that's where we're going to come in here. This is the kind of new stuff here. I'm calling this direction positive. So let me do some of my torques on here. This would be a positive torque. Consider anything that wants to get it to rotate this direction is positive. So I'll go T times the lever arm of R. So that's T1 times R, that's plus, minus T2 times R, and then that should be equal to some of the, I'm playing with some of the torques, is equal to I alpha, should be the moment of inertia of this thing, so that should be a 1/2, let's just call it big M R squared, that's I, times alpha. One thing I could do, this alpha, should be is equal to A over R. This often gets used when you have a capital R. So I'll put that in here as A over R. And then the same kind of pattern that showed up a minute ago. This R cancels with one of these. These 2 R's we could factor out and cancel with this remaining R. And so I just end up with T1 minus T2 is equal to 1/2 big M, the mass of the pulley, times the acceleration of the system. So I've got that. So I've really got 1, 2, 3 equations and 3 unknowns. I don't know T1, I don't know T2, and I don't know the acceleration. Probably the best way to go about solving these simultaneously is solve this one for T1, take and solve this one for T2, that is just arrange it so T2 is equal to something on this side and T1 is equal to something on that side, and then substitute it into this equation, and then you should be able to get what the acceleration is. Okay, is that too sloppy? Okay, and again, the details I'll let you work out. I mainly want to get in how we set these things up and how we're going to start to tackle the problem. Okay, so that's this. Let's do one more that's kind of fun. How are we doing on time?
Hey, Don,
yeah.
What is there a sign for the sun convex?
This here,
Yeah.
T, a sine.
Sine 37, is that from the block?
Oh, the incline was at 37 degrees. I'm dealing with the force of gravity that's pulling along in this direction. So the force would be 5 times G, and then I want the component down the incline.
Yeah, so it's just your normal, right?
There would be, let's say, there's also a component this way that it would be balanced. So I'm kind of leaving out the normal force and then also this component. They're there, but they don't lead to any kind of motion. If I had a further complexity with friction here, then I would definitely want to include this to solve for the normal force to determine what the frictional force would be. And then that would be included in this.
And then one more thing. Why do we have T multiplied by R there for torque? You see where you crossed out the R?
Okay, yeah, okay. Torque is the force, the tension is the force, and the moment arm is going to be that lever arm. So think of it again like a wrench here, and the force applied to that wrench.
Right.
Okay, that's going to be our torque. So yeah, I do have that. So I hope that makes some sense to people. Okay, let's try another one. On these extra problems, how about this number 3? These are definitely trickier. And let's see, you got. Let's see, I guess for you it would be like this. Kind of a slope. Let me just kind of get to this idea. We've got like a spool, like adding machine tape. And okay, I'm going to put this thing about in the middle of this thing. And what's going to happen is the tape is going to go over a pulley. Maybe I'll do a kind of a general drawing first here, as they have it in the book. Okay, so we've got this incline, and they've got 30 degrees. I'm going to exaggerate that. Seeing these angles, again, generally kind of exaggerate your angles a little bit, either steeper or shallower. And this pulley up on top, though, is one of these massless, frictionless pulleys. So he's making it a little easier on us. The tape on this thing, let me indicate that in kind of green. This is kind of the trickiest thing to see. That should be running parallel to the surface. It's going to hang down, and it's going to hang on to another mass. And okay, and actually we got to set this thing down here a little bit, because this thing is, he says, is going to roll down the incline. The math should show us that. So it's going to go down something like this. And it's going to wind this paper up. So again, this tape is like this. And one thing you want to look at in terms of, first, the displacement. We've got kind of some weird things happening. Look at the end of my hand is at the end of this thing. This green mark, I think, is about in the center. And if I let this thing go down the incline, it's rolling and pulling this along and also winding it up. And so when my hand gets to the green mark, that's from here to here, this started at the green mark, it moved half as far. Okay? A lot of these tricky relationships, it's best to try to see in terms of a displacement. The idea is, if this thing is going to go down, one, it's got to go this far this way, but also it's got to wind up what I had. So there's a difference in displacement between these two. Let's call this displacement, let's say it's going to go up some. Well, let's say as this thing goes down, I need to give myself a little more ramp here. When this thing gets down to, let's say, here, and it's moved through some distance, let's say this is x1 that this thing moves. As it moved, this x1, or I'll call this x2, is going to go up. This amount, as it moved from here to here, had to pull some tape. So there's x1 here, and then this thing would have had to gone up. Uh-oh, better get lower. Down here. Would have to go up that amount, and so it would go up x1, just the displacement of this, but also we're wrapping x1 around here, so there's an additional x1, and it had to pull it from this thing, so this thing goes up twice as far, x1. So I would say x2 is equal to 2 times x1. And that's how you kind of want to look at these things. They can get very tricky, but look at it in terms of what I'm saying is displacements. Then once you have that, you can take the derivative with respect to time. Taking the derivative of x2, that's going to be, let's say, call that v2, is equal to 2 times the derivative of x1. That's going to be v1. And then if we're dealing with accelerations, we can take the derivative one more time. The acceleration 2 should be equal to 2 times the acceleration of the first one. So that's probably the trickiest thing in the problem to see. Now, there's this is rolling without slipping. There's let's see. I think I'm going to draw a little bigger picture of this thing on the incline. Kind of a free body diagram to it. We've got the circular wheel, and it's on this incline that is at 30 degrees. And through this thing, now here I think we can call the tension on these things. We're going to have a tension back in this direction. Let me indicate it here. So this is going to be tension T. And I don't need to concern myself with T1 since I've got an ideal massless frictionless pulley. I'm going to have the same tension applied to this. So that's like the good old days. That's just going to be the same. I've got, now this is going to roll without slipping. Is there going to be some friction involved with that? Okay, if it was slippery, this thing would just tend to slide down the incline in pulling this thing up. If I want to get it to roll without slipping, that's going to take some friction. I'm going to need to get this thing to roll. There's going to be some friction on the roller that's going to be back in this direction. And what's getting it to come down this incline is going to be the gravity of this thing, mg, pulling it down. And these are the forces that are acting on it. If we're going to call the x-axis, let's say, along and parallel to this thing, so it's moving, again, the motion on this thing is along this inclined plane, and so this axis is going to be at an angle. There's going to be, I got to get a better look here if I'm going to screw this thing up. This is going to be, again, mg. And then I want to get a component here that is down the incline. So hopefully this picture is adequate. This is going to be 30 degrees. And I want mg times the sine of 30 degrees is going to be this force down the incline. Let me kind of put my forces here. Some of my forces, and I'll call down positive, getting ahead of myself, is going to be mg times the sine of 30 degrees. 30 degrees. Okay, that's going down the incline. I've got the friction and the tension holding me back, minus friction, minus the tension. And that's got to be equal to F equals ma. That's going to be the mass of this thing times its acceleration. And we'll call it A1 for that roller. And so that'd be the forces on that. Now, also, we have the torques on that. The torques are going to be, I'm calling this direction positive, so I'll call this motion positive motion in that direction. Consider what forces want to, so I'm going to do now the sum of the torques. First the sum of the forces, sum of the torques. We've got, and I'm doing the torques around the center of mass of the wheel. That's important that I'm doing that. And kind of locked looking pictures. This is going to be R. I'm going to get this tension wants to get it to rotate in the negative direction. So I'll put minus T times that R. Okay, that's going to be that. Wanting to roll it up the hill. the friction wants to roll it here down the hill, and we need that. So this friction, even though it's pointing this way, it's still, imagine pulling here, it wants to turn it this way. This is going to be a positive torque. So that's going to be plus friction times that same R, and that will be the torque. mg is pulling right at the center of this thing, so it is right at the center of mass. Its radius is 0, so it is not helping to rotate this thing. It is a force that wants to drive things down the incline, so it's not like it has no influence, but it's here in the force equation, but it has no effect on the rotation of this object. And so that should be equal to the moment of inertia of this thing. Let me just call it I, and it's going to be times alpha. And so we've got that equation. Okay, so from this, I think a lot of ways we can approach this, but I think it would be best to solve this one between these two equations. Solve this one for F. So I'll take this over to the other side, and let me write this out and see if you're okay with it. Here, I'm going to then plus T times R, and then I'm left with F over R. I'm going to divide through by R, and that will be the friction. That came from the rotational thing, and now let me put that back up into here. So let me run over here. mg sine of 30 degrees minus the friction, minus I alpha plus T over R, all over R, minus T, yeah, T is equal to MA1. Okay, oof. It's messier than I thought. Okay, so they give us the masses of these objects. The thing we don't know is the tension, and we don't know the acceleration. That's where we're going to want to tie it into this other object. And let me take this over here. In terms of the motion of this, let's say we call this the plus direction. So this is plus going up. And so I would say on this piece, I've got the tension pulling up. The weight of this thing is going to be M2 times G pulling down. So I'll say for this one, the sum of the forces are going to be T, the tension, minus M2G has got to be equal to this one's mass, M2, times the acceleration. Oh, this is now, we want to be careful with this. This is going to be A2. But we have this relationship that these A's are different. This is A1, this is A2. So I probably want to change this, and what I guess I'd like to do is my two unknowns here, the tension, I'd like to solve this one for tension. So let me kind of do this at the same time. So T is equal to, take this over to the other side, is M2 G plus M2 times A2, which is 2 times A1. And so I have this from the forces of that. Then I can take this and substitute it back into this equation and solve for A1. Okay, or I should say you should do this. Okay, this is a tough problem. I mainly want you to see kind of the strategy in setting it up. Yes? Over here? Yeah. Okay. First off, all of. What's that? Sum it up? Yeah, sum everything. Okay. Yeah, this part is actually, the older part isn't too bad. First of all, did you get this idea about the displacement, how we're rolling up some of this? And so the fact that this weight is going to go up as this thing goes down at a faster rate. My hand is going to go over to this green bar. That means that had to come up this far just to meet that. Yet this only went down half as far. So these get to be tricky, but the idea of a simple kind of displacement first, that this moves twice as far as that one moves. Once I have that, that's the easiest way to kind of put it together. And then taking the derivative, if it does that in the same delta t, this has got to go from v2, it's got to be 2 times v1. And also, if we take another derivative, a2 has to be equal to 2 times a1. So this is all due to this kind of the complicated nature of this roller. Yeah?
Where is your x of 2 on that picture? Because I don't see it.
Oh, yeah, yeah. Yeah, I apologize. Yeah, I was kind of alluding that this went up at x1 as this thing came here, and then it rolled up another x2. So x2 means this would go up this far. It'd be kind of this plus whatever we wrapped around. And so, yeah. A lot of nastiness here. So if you can kind of put this together, this is good practice. This definitely killed people on the exam. Yeah. Yeah. He does that from time to time. Could be you. Okay.
This one did not die.
I'm sorry, I missed that.
Why did you include F and this one did not?
Oh, this one, actually I've got both sums of forces here. So.
And in the other question, question 5, you had F going that way in the picture, but then it was no F.
Are you saying I screwed up here?
No, I got confused. I thought that was a force, and he said it was friction.
Oh, yeah. This is this part. Yeah, this is the actual friction. We need to have that. If this was slippery, it would just kind of slide down the slope. It wouldn't be forced to roll. Now, I'm not quite sure what that friction is, but it's necessary where he says it rolls without slipping. We would, and you'll notice that between these two equations, I solved for F and I eliminated it between those two. So the friction is tied in. One, it wants to hold this thing back. It wants to slide down here. It wants to hold it back, along with the tension wants to hold it back. Gravity wants to drive it forward. But now that friction has two roles. It also has the role that this is going to roll without slipping, so that force is wanting to get it to torque, and that's why it is in the torque equation. We do have both the sum of the forces. We've got F equals ma. That's all three of these forces. This force, and a little component of gravity down the incline. That is equal to mass times acceleration. But we also have the idea that it's rotating. So that is these torques minus T times R. This tension wants to roll it up the incline. So this is the plus direction, this is the minus direction. The friction, it wants to roll it down the incline. It's actually pulling, and we need that to get this thing to roll. And so that's positive, that friction. And then that's equal to I times alpha. So so I solve for friction, and I put it into this equation. I've got a bit of a mess. We can simplify that, but it's algebra. So really, from these two, I get this one. That's all based on this information. This one is the simplest one to really deal with, because now we just have these two forces. We've got the tension minus the weight of this thing is equal to its mass times acceleration. So all of these are in play. We've got essentially, when we put this into here, we had two unknowns. Now we just have one unknown. We can solve for A1. Okay? Yeah.
Will all the R's cancel out?
Oh, yeah, likely. I kind of, actually, if you look at this one, that friction, I could have canceled an R with this, and then I would be a 1/2 m r squared, but I'd be dividing by r plus t. This would knock off with one of these. The other one, when I substitute for friction, actually, I take that back. I think one of them is still going to be in that when we substitute in. So I think the I will have an mr squared. I'll have an r squared that'll knock off with one of those, and this again would knock off with that one. But we'd only get rid of one of those r's. Yeah, I'm wondering. In fact, he gives you that. He says, okay, the cylinder, that's this thing, is 50 pounds or 23 kilograms, and he has a radius of 7.6. So he definitely would need it. Yeah, a lot of times they do just drop out, but not always. Okay, so
is assuming no slipping the same thing as saying frictionless?
You can still have friction. For instance, let's say your car tires are skidding. They could still be turning, but that frictional force is the rubber on the road moving.
Right.
Rolling without slipping would mean that it's really static friction. This friction doesn't do any work because it's not acting through a distance. Some subtlety. I hope to get to another problem maybe that kind of touches on some of those issues. And in fact, the very last one on the extra problems, if we have time to get to it, we'll get to some of those issues. Yeah.
When you're substituting for I and alpha, can you do what you did before and do the A over R as alpha?
I'm missing your what?
So you have alpha is equal to A over R and the other problem. Can we do that here too?
Oh, yeah, if you could turn this into the angular acceleration of that down. Yes. Yes. You would just say this is equal to r times alpha and divide through by r. I guess I should use capital R. And so alpha is just A1 over r. And that would be alpha 1, the angular acceleration of the. So, sure. And it could have been asked that way. Okay. Wow. There's a lot of stuff in here. Let's get a little more variety in here. Let's deal with the idea of, introduce the idea of angular momentum. Okay, and okay, the idea, let's say we've got a rigid body, and let's say it's rotating with some omega. And again, think of it as made up of a whole bunch of pieces here and that are all rotating with different velocities. Let's say this is m sub I, this is v sub I. And we can use the idea of angular momentum. It's defined to be a vector r cross either mv or r cross p. I'm putting both here. And this, I'm going to put 3 lines. That just defines this thing. So it's not a matter of, hey, prove this. We're just going to give this and give it a name and show that it's useful. First of all, we can deal with the angular momentum of a single piece. That would be this r, and this would be the r sub I. And so I can get the angular momentum of this first piece, r sub I. That's going to be cross the velocity of this piece, m sub I times v sub I. And v sub I, in terms of v sub I should be equal to the r R sub I, I'm starting to fry here. R sub I times omega, okay. Now in terms of, usually we'll do this in terms of absolute value. We'll say that L sub I, or by absolute value I mean magnitude, will be R sub I times M sub I times V sub I, which is going to be R sub I times omega. So this would be the angular momentum of that piece. If we wanted to get all of the angular momentum, well, let me leave this here. I'll get the total angular momentum is going to be equal to the sum of all the individual angular momentums, and that would be the sum of, let me have this is going to be M sub I times R sub I squared times omega. And again, we have this piece here. We've seen that before. That is what? Moment of inertia. That's the I times omega. I was able to factor out omega because, again, for a rotating object, they all have the same omega, even though they have different V's. So this is the rotational angular momentum for a rigid body rotating around this axis. Now, you'll notice I dropped out these vectors. We're not going to do anything real formal with this. Formally, if you've had some math in the cross product with that, we would say R sub I, we put those two together. And let me just kind of indicate, I don't want to dwell on this too much, but let's say R sub I is out to here. V sub I is going to be, I put them tail to tail, so R goes out here, V is in this direction, and then R cross V would be like this. It's going to be out of the page at us, or out of the board. This wants to define the axis of rotation around this thing, the cross product, and all of these things are all moving here, so even a piece down here, its R is this way, the velocity is this way, R cross V is still out. Every one of these things has its vector pointing out, and that defines the axis of rotation of this thing. For us, we'll just do it in terms of absolute value or in terms of simple magnitudes, because we're dealing with relatively simple things that are just rotating in a plane. If you've got something rotating in 3 dimensions or tumbling in space, it's very, very powerful to start to use this more formal symbolism. But again, we'll just kind of simplify for an object that's rotating. Its moment of inertia times whatever speed it's rotating will be its angular momentum. Now, this definition of angular momentum can be used straight off in a way that is kind of counterintuitive. Suppose I have an object that is just going through space, and it's some mass, and it's going through space. It's just going to travel in a straight line. So we say it has linear momentum, and a linear momentum is conserved. It just keeps going through space. Now, if I said, well, can this thing have angular momentum? Most people would say, what do you mean? It's going in a straight line. It's not rotating like this disk was rotating. How can you say anything? But we can just say this is the definition of angular momentum. I can go ahead and apply it. I kind of should have get a little ahead of myself here. The magnitude of that should be L is equal to R times P, which is MV, and with the cross product we should have the sine of the angle between them. Kind of forgot that, mentioned that. We're going to use that here. We can do the angular momentum about any point in space, and it turns out if it's traveling in a straight line, we can just pick a point, pick any point you want, and deal with the angular momentum for this thing. This, let's say we're back over here. The initial angular momentum is going to be the initial R times M V initial times the sine of the angle between them. So the initial R would be this supposed to be at my point here. So this would be out to here. This would be R initial. There would be some theta, maybe I should call that theta initial, because as this thing goes through space, it's the R is going to be changing as well as the theta is going to be changing. It should be standing with the same V, but the R, let's say this is R final, is going to be this. We would put them R and V tail to tail, and I'm going to get kind of an angle. This is going to be theta final. This is theta initial. And what I can do is show that, and this should be L final. That should be just R final times M times V final times the sine of theta final. Now what I can do with each one of these things, as this is coming across here, theta is changing, R is changing, so it looks like we don't have conservation of angular momentum. But if we take this thing and it'll go R initial is equal to M V initial, and I'll group R initial with sine theta initial, this quantity is going to be related to something we refer to as this, I'm going to call it R perpendicular. The idea is that there has some line of action that this thing is moving through. As it moves through there is some distance from that point that we're figuring the angular momentum is from to that line of action. We're calling that R perpendicular. Now if you look at R initial times the sine of that angle, that is R perpendicular. MV initial times R perpendicular is L initial. And I can do that over here too. I'm going to say that R final, I'm going to go M times V final, R final, group it with the sine of theta final, and this is nothing more than M V final times R perpendicular. Now, called V initial and V final, that conservation of momentum, that should have stayed the same. I shouldn't even put those subscripts on there. So the idea of this is that if you've got something with linear momentum, it has angular momentum about any point. And if we choose this point, again, all it matters is that we have a speed mv, or its momentum, times that perpendicular distance will give you its angular momentum around that point. And you don't have to get into these complexities. I think as we apply this, hopefully you'll make some sense of it. Okay, let's try a problem that is I'm thinking on not this one. Okay, on the practice test, the practice problems, I'm thinking of number 6, the clay ball and the meter stick. Or let me clear off some room here. As you take a look at that, number 6, we've got a half kilogram clay ball traveling at 3 meters per second along the x-axis, coming left to right, and a meter stick coming up to collide with it. And kind of the beginning picture is this clay ball. It's got this moving along, it's coming along this way. We've got a meter stick that's traveling. Okay, first of all, let's see. We got, this was 3 meters per second. This clay ball is 0.5 kilograms. It's going to come up. This meter stick is moving along at 4 meters per second. And that was, what was it, 0.25 kilograms is its mass. So it's going to come up, and as this meter stick gets, as the clay ball gets over there, it's going to somehow, it's going to skewer this thing. And let me kind of change colors here. This was blue. Let's see if I can go to, where's my green? when the meter stick gets up here, the clay ball has come and they've collided. So this is the clay ball on the end of the meter stick. And this, let's kind of indicate what's going to happen there. So again, the clay ball's coming along, the meter stick's coming up. They come into one another and somehow stick magically there. And then what's going to happen then?
That's the inertial so.
Oh.
No, they're going to rotate and leave.
Yeah, it's actually, going to rotate and translate. The idea that the two of them together should have some position of the center of mass, something about there. And the idea when this hits, it's going to, see if I can, without killing myself, it's going to start to go like this. Okay. In addition to that, how about conservation of momentum, just linear momentum? Yeah, so actually these two are coming in, so in terms of there's a momentum this way, a momentum that way. The final momentum I expect to go off at an angle, and I'm going to allude to that there's going to be this center of mass of the system, and that it's going to move off at some angle that we want to find, that is the center of mass. Think back to that hammer I was about to throw. It wants to rotate around its center of mass, but then also it will translate. Its center of mass would move in a straight line off this way with the velocity of the center of mass, so it's going to do that. And then also it's going to want to rotate around the center of mass, so that's going to be its omega. Okay, now for the first part we have the idea of conservation of linear momentum. Momentum. And here we would just say what is the initial momentum of the system. The initial momentum is, well, I've got this in the x direction. 3 meters per second times 5 kilograms is 1.5 kilogram meters per second in the I direction. Okay, and let me call. And then I've got this in the j direction. That's going to be plus the meter stick was 1.25 times its velocity of 4 meters per second. And that's in the j hat direction. That's the initial momentum. Then they're going to go off in some direction. That's going to be P final. That should be equal to the total mass of these things. This was 0.5 and 0.25, or did I get that right?
Yeah, it's 0.25.
0.25. So that's going to be in fact, I screwed up this, right? Where did I think I got that from another problem. Let me, yeah, 0.5 and 0.25 is, yeah, this is going to be 0.25. Now it's the combined center. They're really stuck together. So we're going to have a 1.75 is going to be the mass times the velocity. And we're going to have times the cosine of theta would be in the I hat direction, plus 1.75 times v times the sine of theta in the j hat direction. Now maybe you can go ahead and handle these things. I'm going to put these two things equal. These two things are going to be equal. I think you can handle this. We did something earlier in terms of conservation of momentum. You should be able to get both v and get the angle. The trick I showed you before is take the sine of this and divide by the cosine to get the v's cancel and you get your tangent. I think I'm just going to leave this. You can do it. The trickier part is the idea of this rotation. We want to get the angular momentum here. Now, a look to the future is important, that when these two join, the center of mass is going to be in here, and it's going to want to rotate around that center of mass. we want to use conservation of angular momentum. The idea that there's going to be forces that are going to be internal. Those torques are going to be internal and will cancel out. And so that the overall angular momentum will be conserved. So the idea is the angular momentum is going to be conserved, but it's going to be conserved about what? The center of mass. This is what it's going to rotate about. So if you think about this one is a straight line, it's coming in a straight line back this way at 3 meters per second. And it's what we're going to call this R perpendicular. Think again to this idea. It's coming in. The R perpendicular, the point of that I want to deal with my angular momentum is from the center of mass, because that's what it's going to rotate. So what I would say is the initial angular momentum of this thing is going to be 0.5 kilograms times v, 3 meters per second. But I've got a times in r, let me just put it as r perpendicular. But I need to find out what that is. So what is r perpendicular? Okay, but in order to figure that out, I need the center of mass. So, you have to calculate where the center of mass is. So let me, I think I can do it right here. Okay, so let me kind of do this on the side though. Let's say we've got a meter stick. We're going to connect this clay ball. And when we do centers of mass, what we need to make an origin. And I guess in my notes, maybe I'll follow that here, is I'm going to make my origin, put my x and y axis right at the center of the meter stick. And that means I'm just going to be doing all my measurements relative to that point. So what I can do is the clay ball's up here. And so once I choose that, I can say, oh, the y center of mass of this thing is going to be the sum of all the individual pieces, m sub I and y sub I, all over the sum of m sub I. So y center of mass is going to be the meter stick, which was 0.25. But where is that located? Its center of mass is right where I put my origin. So this is kind of convenient. So that's times 0. I can do that. And then plus this other clay ball, which is 0.5 times its radius. Well, it's half the meter stick. Let me just call it L over 2, just kind of get those ideas. And then we'd over the total mass, which is 0.25, and 0.5 is 0.75. So I can immediately get y center of mass is going to be 1/3. 1/3 L, or 1/3 of a meter. So if this is a meter stick, the center of mass is 1/3 L up to the center of mass. Now the thing is, we want this distance is r perpendicular, and this is a half a meter minus 1/3. I would say r perpendicular is 1/6 of a meter. So I had to do that to get that. And so I can put that in here. So this is 3 times this is 1.5 times r perpendicular, which is going to be 1/6 of a meter. And I can come up with the initial angular momentum that's just the clay ball. Is coming in. I also had, before I okay, this is just L initial of the clay. What about the meter stick? It's coming in here too, isn't it? Ooh, yeah, it doesn't have any angular momentum. Now it's traveling in a straight line like this, okay, but we would take it as mv times r perpendicular. What's its r perpendicular? Well, it's going right through that point. And so L initial for the meter stick is going to be its mass of 0.25 times its velocity 4 meters per second, times its r perpendicular of 0. Okay. If you don't like that argument, you could also say that r is coming here and mv is in the opposite direction. They differ by 180 degrees. So if you want to use the sine of 180 degrees, that's still going to be 0. So the idea is that the angular momentum is just due to the clay ball. So the initial angular momentum is just this, whatever this turns out to be, 1/5, 6th, whatever that turns out to be, is the initial angular momentum of that system. These two things as they approach one another. Whew, okay, now we're not quite there yet. We need to get the final angular momentum, and that's going to be the idea that they're going to rotate around this common center of mass. So again, this meter stick and this clay ball are going to be rotating around this common center of mass as that center of mass goes off. This distance is 1/6 of a meter. What we'll use is that this is going to be the I of this system times an omega, final omega of this thing, and that's what we really want to find, is how is this thing rotating around this thing. The tricky part is the moment of inertia of this thing. One, we've got the clay ball, just a mass going in a circle. That's going to be equal to the mass of the clay ball, 0.5, times the radius of the circle, which is going to be a 1/6 of a meter, 1/6 squared. So this is the clay. And then we're going to have to add in the ruler. But now the ruler is not rotating around its center. We're going to have to come up with the, this is going to be the I of the system that I want to find. Is going to be, this is the clay ball. Let me write this out for the rod. See if I can write better than I can talk. I'm going to use the parallel axis theorem. It's going to be 1/12 ml squared. Of course, it's just a meter stick, plus the mass of this meter stick times the distance from that point of rotation to the middle of the stick. But that was, we determined from the center of mass. Very important information here. 1/3 L. So that's going to be L over 3. We're going to square that. And so all of that is going to be I of the system. So once I have that, now I can go ahead and use conservation of momentum, angular momentum. I've got L initial is going to equal L final. So I bring in L initial here is equal to L final. That again is going to be the I of the system times omega final. So whatever I get here comes back into here, and then divide through, and then you're easy and home free then. The omega final would tell you how that thing is rotating. Okay, so let's see. So think about that for a moment. Let me just look and see what other things we're missing. Oh, we haven't done a equilibrium problem, and he's got one here. We're going to run a little low on time, but let's. Where is it? Oh, here it is. Number 8 on the practice problems. We're going to have a statics problem. Statics is. So let's do one more example. Let me give you something that, even though this is a relatively simple statics problem, and maybe you're doing well with all of these, some of them can get tricky. And something that is very important as far as calculating torques. Let's go back to a simple idea. The idea I started off with, the idea that, you know, if you want to think of torques, we'll think of like a wrench. And you want to apply that force perpendicular to the handle, all right? You're going to have some length of the handle we'll call R. We apply the force perpendicular to the handle, and I think this is the most intuitive ways of thinking of that torque or that twist. Torque is going to be equal to R times F perpendicular, and so this is a good one. Generally, though, the forces aren't lined up so nicely. They're maybe off at some angle. So let's say this is the actual force, and we could break that force up into two components. One that's perpendicular. And I go parallel. This is perpendicular to the handle. There's also a component of the force that's parallel to the handle. Now, does that lead to any kind of torque? This would just want to pull the wrench off, or if I put it in, is going to go in. So we really don't care about a force that's perpendicular to the handle. If I've got some angle theta, and that theta is defined to be the radius, the tail of the radius together with the force, the smallest angle between them is the theta. Then we can write the perpendicular component. The torque is going to be just F times the sine of theta. And this is the most general way of writing it. Now, here's something else, though, that is very powerful in doing statics problems. Can take the difficult problem and make it simple. Is this idea, and it's not intuitive, but it makes mathematical sense. We take that force and imagine it acting along, we say it's line of action. And there's going to be this distance between that line of action and the pivot point, and that, let's call that R perpendicular. Okay? And the idea is, if I take this and turn these terms around, they're the scalars, that's going to be force times R times the sine of theta, and group those two together. This is the torque. If you think of this angle theta, this is also going to be theta, and we go R times the sine of theta is R perpendicular. So torque is equal to F times R perpendicular, and you've got three ways of calculating the torques. And very often this is the one that's a lot easier to apply than these, although any of these three, depending on the situation, you're free to use. Let's take a look at this sign, this number 8. And we've got, of course, the wall, that's in equilibrium. We've got this some kind of bracket and a pin, and we've got this beam hanging out here. And we've got a cable coming over here at some angle theta. He says, okay, the uniform sign of weight W and width L, 2L, hangs from a light horizontal beam. So I guess we're just kind of considering that that is no effective weight to that. That on the sign over here, as it's supported, coming here, and he says, okay, he gives us the width of this, 2L, and we've got this distance between here and here. He defines that as D. Again, that's 2L. Theta, let's see, what else have we got? Okay, determine the tension in the cable and the components of the reaction force exerted by the wall and the beams in terms of W, D, L, and theta. So he doesn't give us any numbers, but we should be able to come up with an expression for this. Now, did he tell us how tall this sign was? No, he didn't. Now, it should be that in the sign, the center of the mass is like here, and we can't really determine it because we're going to want to get the torques, and torques are around some point. I'm kind of jamming through this too fast here. Let's look at some of the forces that are acting. We're going to have, of course, mg of the weight of the sign pulling down here. I'm going to kind of do this as a whole picture. We could break this into individual pieces. There's going to be a tension. Also, this pin here has the ability to apply forces in any direction. And consider that we'll just immediately break that up into components. Let's say one, call this R sub x, and a reaction force, and then a reaction force in the y. We've got those two forces. And we've got gravity. Now you could also say, well, I've got forces in here, but I can deal with the fact that the whole thing's in equilibrium. I don't have to take it apart, although you're free to do it as two separate bodies. But the idea that they would be internal forces, you're pulling on the beam here and pulling here, this action-reaction, they would be internal and they'd cancel out. So we can do it with just this kind of picture. But the idea is the thing is static. It doesn't translate, move around. So the sum of the forces in the x have to be 0. And the sum of the forces in the y have to be 0. And that's kind of old stuff for us. The part that's new and the part that's powerful in doing these problems is we can do the thing doesn't rotate, meaning that the sum of the torques have to be 0. And now the sum of the torques have to be 0. That's true about any point in space. So we get to choose which points we take the torque around. Now, what would be a good point to choose? Yeah, this pivot point. Why would that be good? Yeah, we don't know what these are, but so what are their moments are their lever arms? 0. Yeah, they're applied right to here. If you think of these forces applied, they're not going to do anything to twist this thing. If you look at this thing, this mg wants to pull this thing down, and the tension wants to pull it up. Between these two, they're in a sense holding it. We'll need to solve for that tension. So I want to do the sum of my torques about point P. Now, here's where I can, again, I'll go Rx times 0 plus Ry times 0. That's there. We can, and I'm getting ahead too, that we can choose a direction of rotation we want to call positive. A lot of people, like in the math class, will say, well, we'll call this rotation positive, and that's good. So tension wants to get it to rotate in the positive sense. And so I could say that this would be plus, and this is where I'd want to use maybe this form because I have a clear angle there. So the R would be the length of this thing. Well, let's see, he puts it as 2L plus D. That would get me out to that'd be the length of the beam. So that's D plus 2L. That's going to be the length of that thing. That's R times T times the sine of the angle between them. And again, they just call it theta. So that's going to be a positive torque. mg, now what am I going to do for that? If I go, let's say this is R, can I get R? I mean, I don't know the height of this sign, do I? So it looks like it could be a problem. But that's where you want to come back to this idea. And I've got this one example is that my force here applied here. I could, if I was given the height of this thing, I could maybe go figure out this R, figure out the angle, and then I could do this this one with F times R times the sine of the angle. But I can use this idea that I can move my force along its line of action and apply it at a point that is perpendicular to my force. So this is R perpendicular. And I would, in a sense, be putting my force up here. That force, mg, is the same pulling from here as it is up here. So I'll call that a negative torque. That's going to be minus mg. It wants to rotate it this way. And that R perpendicular is going to be just d, this little d, plus one of these L's. And I'm done. Then I can set that equal to 0. And let's see, he wanted to determine the tension in the cable. So basically, arrange this thing so T is equal to something. Of course, he doesn't give you any numbers, but of course, these two terms go to 0. And you can solve for T. Once you have T, there will be T in the X, which is going to be T times the cosine of theta. Actually, it's in the negative X, so that's that way. And T in the Y, that's going to be T times the sine of theta. That's when I can go back and take these into my sum of my forces in my X and Y and solve for my reaction forces. This is pretty straightforward, where you just sum of the forces in the X. Tension has one in the negative. It's going to be balanced by this reaction force in the X. And then these interplay here is going to lead to a force in the Y. Okay, so that's kind of a simple statics problem. I realize you've got some trickier ones, but hopefully you get a bit of a sense of it. The physics isn't too difficult to understand. The idea that it's an equilibrium, the sum of the forces are 0, the sum of the torques about any point are 0, and then it's a matter of solving for your unknowns. So, whew, okay, a lot of stuff. Study hard. We're almost there. Okay, and I'll stick around a little while if you have some questions. And anyway, good luck. Okay.
Thanks, Tom.
Okay, you're welcome. Boy, you guys got a lot of stuff. I'm sure glad I don't have to sit down Monday morning.
I just wanted to know, so like, you mentioned the tangent